25 GHz signal integrity analysis is now available from Pico Technology with the PicoScope 9404A-25. Like a sampling oscilloscope, the PicoScope 9404A can analyse signals far beyond Nyquist. Unlike a sampling scope, the 9404A captures data using random sampling, similar to a real-time oscilloscope with the addition of an incredibly low jitter analog trigger. That allows it to capture high-speed signals without the need for an external trigger source or a clock recovery add-on. The extended real-time trigger circuit uses the raw, unprocessed signal to trigger, allowing high-accuracy triggering with industry-leading jitter of just 1.5 picoseconds. Moving on to the specifications, the PicoScope 9404A-25 has a maximum bandwidth of 25 GHz with a random sample rate of 5 terasamples per second, providing a transition time of down to 14 picoseconds. The front end has 4 25 GHz channels, each utilising a 12-bit 500 megasample per second ADC with plus or minus 800 millivolt input range. The rear includes USB and Ethernet I/O, optional clock recovery options, and DC power input. So what is SXRTO? An SXRTO utilises a similar trigger method to real-time oscilloscopes. As the main ADC collects random samples of the repeating input signal, the raw signal is also diverted to an analog trigger circuit. This trigger module uses the trigger point as the reference and organises the collected samples to build a low jitter representation of the high frequency waveform. For repeated signals, this significantly reduces the delay between the trigger event and the acquired samples, making it better than a conventional sampling oscilloscope for most applications. Another benefit of the SXRTO is that you can trigger using a single input signal without the need for an external trigger source or an additional clock recovery system, which most sampling oscilloscopes make use of. So let's dive into a quick signal integrity demonstration using the PCI Express signal into the 9404A. First, power and connect the PCI module to the 9400 using a single channel input. Next, similar to any real-time oscilloscope, we'll set up the signal to make it visible. And then we'll add the PCIe mask. Then you can see the eye diagram of your PCIe signal, with the built-in mask assessing the signal integrity of the signal.